I have entitled my talk, The Amazing World of Two-Dimensional Materials, because I'm not only going to talk about atoms, but also I'm going to talk about different scales and different levels of complexity, which I have seen you are interested in. And some things we can collaborate. In fact, we have already started the collaboration. I mean, I have been just for not long time, so it is really very exciting to be here. Please call me Humberto. If you call me Professor Terrones, I will not. I don't understand, okay? My name is Humberto. Okay, I will start with 3 quotes by people you should know, and if not, then after this talk, you will know. First one is by Democritus, the quote. He lived like 90 years, but I believe at this time they didn't count very well because it was unusual to live 90 years. Everything is made of atoms and empty space. All else is opinion. Do we agree? Of course, right? The second one by William Kingdon Clifford, a Scottish mathematician. And he said, I hold that in the physical world, nothing else takes place but this variation. And he was referring to the curvature of space. By this time, Einstein was born in the year Clifford died. And I mentioned that because of the curvature of space. And the third one is by Einstein. The human mind has first to construct forms independently before we can find them in things. And my talk will be about how can we construct forms and different shapes and very complex structures. Of course, you need to know something, because if you don't know anything, then that would be bad. Lola, there are chairs there. You can bring one. So take this in mind, right? Now I will switch because 2D materials and layered materials have to do with 2 dimensions. And if I ask the question and you think carefully about if something that has 2 dimensions exists that is made of atoms and may acquire curvature, I will tell you, I mean, 2-dimensional materials do not exist, right? I mean, just 2-dimensional materials. What happens is that our atoms have are 3-dimensional atoms, and we know, and particle physicists, they know very well this. So I found this definition, which I'm not happy, but I'm going to use it, are nanostructures composed of atoms in which the thickness is at least 1 order of magnitude smaller than the smallest side. I don't like that, but I have to start with something. And of course, if you are thinking of atoms, I mean, 1 atom thick structures or 2-dimensional materials are graphene and hexagonal boron nitride. I'm going to talk about that, but also this is made of atoms. And the thickness may be 1 order of magnitude smaller than the side. So that's why it's amazing, because I can go with the concepts I am going to show you. I can go from atoms to these and more complex structures, super complex. I mean, we just found that yesterday. So graphite, everybody knows graphite. Graphite will not be a 2-dimensional material because this is made of graphite. Right? This is a chunk. I mean, the biggest rock, I was just walking in the geology department, just trying to see they had graphite, but this is the biggest rock of everything they have. This is a biggest chunk of graphite they have. Of course, these come from a mine, and the graphite has impurities. It's not very nice for exfoliating, of course, I'm not going to exfoliate that. Then there are processes. So, but one layer or two layers, maybe two-dimensional materials, or even three layers, right? Or a few layers, right? So graphene, which is one layer, is hexagonal. I mean, every atom is connected to other three and forms this beautiful honeycomb that this, I would talk about, because yesterday we were talking about with Eugenia about bees, right? So I'm going to mention that. So it is, I advise, and this is an advice, all the professors here to have lunch with the students, really super productive. I mean, they ask the questions and then you have to solve the problems. I mean, this is a STM image of graphene. You can see that, yes, it's hexagonal and every vertex is connected to other three. And we know that graphite or graphene are soft materials, conduct electricity. You know that graphene has very interesting electronic properties, and graphite is a solid lubricant. But you have to be in air. In vacuum does not work. I mean, I like to study the history of science because it turns out that we rediscover things. And then, my advisor, I have just found this. I mean, this was, if your advisor know the history, know the literature, oh, come on, this was just, I mean, 100 years ago, this was not. But it is good to rediscover things, but also it is very good to look at the history and review the literature properly. When Philip Russell Wallace published a paper, 1946, about the band theory of graphite, what he was doing was obtaining the band structure of graphene. And in the paper, he says, well, I will not consider the interaction between layers because, I mean, I will just consider one layer. Excellent. Excellent choice because van der Waals interaction is not easy, right? But what he found in the paper is that the energy depends linearly K of K is the momentum. I mean, any function, X. E is a linear function of X. Can consider this a constant. And by the way, he was calling C the symmetric points in the Brillouin zone. This should be K, but sometimes physicists change the name of things. And we like that. But I tell my students, you cannot change the name of the Brillouin zone symmetric points because this has been already established. So this is important. Now, you can calculate the electronic properties. It is very important to have in mind the linear dispersion, because if you use the Schrödinger equation, you will never get a linear dispersion. So you have to use another equation, which is the Dirac equation, but you can use DFT, first principle calculation. My student Andres calculated the band structure of graphene. You can see the linear dispersion, energy versus momentum. I mean, this is a straight line. Once you add another layer, that disappears and you have a parabolic behavior. And this is the beauty of two-dimensional materials. One layer behaves completely differently from the 2 layers to 3 layers. Even 2 layers can be very useful, as we know, in superconductivity and things, but I'm not going to get into the details. One of the messages is that there are several two-dimensional materials, not only graphene, but and that these two-dimensional materials come from van der Waals solids. That means solids in which the layers are not connected by chemical bonds. So if they are not connected by chemical bonds, you can use something that is called the Scotch tape method or mechanical exfoliation. Sounds much better, mechanical exfoliation, but it's just Scotch tape. And this Scotch tape, I think this image comes from Wikipedia, and this is the Andre Geim when they got the Nobel Prize, Scotch tape. So it could be good to visit all these, and this is what I have been doing. But before that, I want to visit other, I mean, the way my story of two-dimensional materials started, because I have been able to understand lots of things and propose new structures at different levels of complexity. And I think this is what is fun. Of course, Nobel Prize in Physics in a few first week of October, Nobel Prizes will be announced. Everybody, people working on carbon was happy, and some of them not so happy because they were not part of the carbon community, jumped into the community, exfoliated, performed experiments, and found that the electrons behave super different, right? I always like to observe things, and I advise the students to observe and also talk to people and also professors. At different levels of complexity, if you look around, I mean, this is a skeleton of an echinoderm, which is easy to see because you need an optical microscope. But this skeleton has holes here. And this has holes because these holes were inside there was the soft matter. I mean, this is the skeleton of an echinoderm. An echinoderm is like these things, sea stars and sea urchins. And when you remove the living matter, the skeleton has these shapes in which we can see holes and we can see curvature. And this is curved. And I'm going to talk about curvature, but I'm not going to go very deep because I just want you to give you the flavor. At a different level of complexity, if you mixed detergent with water and a bit of oil, what you can have is structures that may be flat, structures that can be spherical, and these structures that perhaps resemble these ones. But we don't know very much what's the geometry. I mean, we need to know, right? And this is the eye of a bee. So this is for Eugenia, because yesterday we were talking about bees, right? I mean, definitely this is a bee. You take the bee, but don't kill it. Which is very, I mean, you have to use already dead bee. Okay, don't kill bees because now there is a problem. If you look at the eye of a bee with a scanning electron microscope before you cover the eye with gold, otherwise it will be charging, you will see that the center of the eye is made of hexagons, right? And these are hexagons. And then you can cover the plane with hexagons. We know that graphene can extend, I mean, forever when you perform calculations. But these can grow periodically. Of course, the eye of the bee, we don't have bees this size, right? It's very small. It's very small bee. And it turns out that if you look at the border of the eye of the bee, you start having these defects. I mean, these pentagons. These pentagons are super important because they terminate the eye of the bee. So we call defects. I mean, these are certainly defects, but have a function. Is what we will do with two-dimensional materials, introduce defects to have a function or to have another thing. And when you introduce the defect, the eye of the bee curves. So these, in fact, are a bit curved, but the defect makes these to terminate. So what we are seeing at different levels of complexity is that there are flat things, there are things with defects that used to be so more or less flat, and there are different curvatures, and then curves things. And it turns out that we live in a three-dimensional space, right? I mean, I'm going to talk about time because then things get not even more complex, but you have to think harder. We live in a three-dimensional space. Our atoms live in a three-dimensional space. And a fundamental question is, what can exist in three-dimensional space? It's a fundamental question, maybe philosophical, but mathematics can tell you that. There are just three geometries in a three-dimensional space. There are no more geometries. We cannot just, okay, I will invent my geometry in 3 dimensions. You cannot do it. Our space restricts what can exist in this 3-dimensional space. And we have 3 geometries. And at school, we learn this one, Euclidean geometry. If you measure the interior angles of any triangle, will be 180 degrees. But if you do the same experiment on the surface of an apple or an orange, the addition of the interior angles of a triangle will be greater than 180 degrees, right? And oh my God, well, Euclidean geometry does not work here. It's a spherical geometry. And the other geometry, of course, I have put a fullerene, and a pentagon appears like the pentagon of a bee. To close the structure, you need a pentagon. You need, and we are introducing curvature, and you, in this fullerene, this structure exists, C60, and Kelly knows, where's Kelly, everything about C60 and other structures I will show. So you introduce these 12 pentagonal rings to have the angular deficit of a sphere. And you close it. This is known since a long time ago. The next geometry is hyperbolic geometry. And here, if you do the experiment of drawing a triangle inside, on the surface of a horse saddle, it's like a saddle shape, then the interior angles of a triangle will be less than 180 degrees. What's the problem of this geometry? The problem is that I cannot take a surface in this geometry, which every point has one particular curvature and embedded in 3 dimensions. But there are tricks. And the trick is, well, I don't care about what happens in the middle, but I do care what happens at the vertices. And the vertices will preserve the topology. I can take a piece, I can change the surface in the center, but not the angles. And then I can get something very, very interesting, super cool. And you will see what. But before that, I need to do a parenthesis because I need to talk about spherical geometry because Kelly is working with spherical geometry. I came across this paper in 1992. These are fullerenes, onion-like structures. Perhaps in the center is C60. But these fullerenes are very spherical, right? And these have millions of atoms. So I was working with C1500, and I immediately realized that you start having these flat faces. What happens? This has just 1,500, and this one has millions. What is going on? So I talked to Mauricio, who happens to be my brother. We have brothers. We have 3 brother physicists, by the way. And then, okay, defects are going to be the answer. And it turns out that you can introduce pentagons and heptagons together, and I can prove that. And in addition to the 12 pentagons you need 12 pentagons to have the topology of a sphere. You introduce heptagons and additional pentagons, which are pentagons, and then you can have a spherical structure. And I believe that's structure, almost sure that's the structure of this fullerene. So Kelly is calculating now the vibrations of these fullerenes, right? You have the coordinates. And we published this in 1997. And I was talking here with Harry Kroto, who was he discovered the C60. And I remember we took a trip to see whales in Santa Barbara. And he didn't want because he gets dizzy very easy. But I was distracting him. And we were talking about these spherical fluorines. Of course, nanotubes were there. I went to the Forbidden City in 2011. and I saw this. The Forbidden City was built between, well, it took 14 years, 1406, before the discovery of America, right? And then I saw this, oh, graphene, that's good, no problem. But I saw this one. And I asked my late wife, I mean, this should have a defect. It has the pentagons. The pentagons should be there, but this should have a defect because it's very spherical. And my late wife, Lourdes, told me, I mean, perhaps it's here, or they will not show you the defect, because imagine, I don't know what would happen if the emperor comes and sees this horrible defect here. But then I look at the back, and at the back here, you have a defect, and also you have the pentagon here, and you have lots of defects. This is a heptagon, and it's very distorted. And you don't see this distortion in the front. So they knew that they had to distort or introduce, they should have, if you introduce the heptagons and the pentagons properly, you can have something super nice. But of course, at some point, the artists realize, oh my God, this is not hide the ugly part and put it in the back. Now, hyperbolic geometry, how I'm doing with time. Oh, perfect. I have to work with this disk. It's the Poincaré disk. I mean, this for simplicity, because there are no very good ways. But the idea is, I have all these triangles are exactly the same surface. All these triangles are exactly the same, but here at the end are smaller because this is the infinite, circle of the infinite. This is the infinite, but all these triangles are smaller. Are smaller, but are the same, exactly the same. But in this space, look smaller, but are the same. And the interior angles, 90 degrees, 30 degrees, and 45. I'm going to take this piece. And of course, the curvature at every point on this surface is exactly the same, what is called the Gaussian curvature, which I'm not going to talk about that. But you can bring a piece of surface with this angular excess or deficit, because you add 90 plus 30 plus 45, 165. This is a triangle. Normally, we work in Euclidean geometry with 180, so there is a deficit of 15 degrees. But you can join these triangles in the same way they are joined here. And what happens? Well, first, you have to generate these triangles. You generate the triangles with 45, 90, and 30. This is the trick. And then I study crystallography and symmetry and geometry. There is something called asymmetric unit. Everything that you put in the asymmetric unit of a space group, which is space group, every structure that forms a crystal belongs to a space group. And there are just 230 space groups. So you put it in this cell. I put my surface in this cell with the right orientation and apply symmetry operations, and voila. I get this surface. And if I continue applying symmetry operations, in this case, it's not necessary. I just have the structure. I know how to connect cubes and then just form a three-dimensional periodic structure, a three-dimensional surface. And the question is, how complex is the surface? And then mathematicians and crystallographers and solid-state physicists, well, let's do one thing. Let us put, since this part is connected to infinite in this direction, and also infinite in the three directions, X, Y, and Z, you can think of this part is connected to the back, this part is connected to this part, and the top is connected to the bottom, and what you have is a sphere with three handles. So the periodic, the number of handles is called genus, right? So you can characterize the topology of the structure by the genus. Genus of a sphere, spherical geometry, 0. Genus of a torus, you have one handle, 1. Genus of this thing that looks like a double torus is 2. And this one is 3. Here in this site, which is they call holes, and they put holes in inverted commas because this is the number of handles. You cannot, if you make a hole in the surface, you destroy the surface. You destroy the orientability of the surface, and then, so you don't want that, right? So the question is, can I do better than genus 3? And the answer is yes. Everything is hyperbolic geometry. I remember my advisor, students follow the instructions of your advisor, not always, sometimes, because I mean, people are humans. But in general, I mean, you can follow. They have more experience. And my advisor, Alan Mackay, told me, you can find the thesis of Schwartz in Imperial College. It was written in German, but I found these beautiful drawings of periodic minimal surfaces. I'm not going to discuss about the concept of minimal surfaces. I want to discuss what happens to give a flavor of periodic surfaces. So he knew, he was a student of Weierstrass. Weierstrass found a very good way of obtaining triple periodic minimal surfaces, and Hermann Amadeus Schwartz got them periodic. And this was a very important achievement because he found this that has genus 3, as I have explained, per cubic cell. I'm going to change the convention in this talk because it's important. Usually the convention is to use the primitive cell, a crystallographic primitive cell, and this is just to make sense to the some mathematics, theorems of mathematics, but there is no harm if I calculate the genus per cubic cell. So every 1 cubic cell has genus 3 handles. Can I do better? Yes. Remember this name of Schwartz, because it's going to appear. Well, Schwartz found the D or F, D for diamond, belongs to the same space group as diamond, and F because diamond belongs to the phase center cubic group. So it has 2 names. This is genus 9 per cubic cell. The gyroid, which I have here, and Lucia has given, I mean, we tested Lucia's new printer, right? And then she wanted to print other things. And I said, okay, let's print this. So this is, and there is a very nice orientation at the corner, which we call 1-1-1 orientation. You see the holes all the way through. So you can pass this one, which is just to have a feeling. And the gyroid is, that one is 5 handles per cubic cell. But when Lucia, we were talking, and she told me, oh, I'm going to work with foams and polymer. Okay, she started investigating, and people have used the gyroid, the P, the D for mechanical properties, but they have not used these ones. This is genus 13 per cubic cell. And this is genus 35. And there are an infinite number of these surfaces with higher genus, small genus. So she's going to work on these ones because these are, besides everything, super beautiful objects. And I have told Nacho we are going to print something in the metal 3D printer, but this is not what we are going to print. We are going to print something very interesting, but I will not show what we are going to print. But there is an infinite number of surfaces. So infinite number of possibilities. And these structures, I was talking to Lola yesterday, and because she showed me a gyroid. And these structures also may have some interesting application for implants, bone implants or something like that. Right? Okay. I'm here with Alan Mackay, my advisor, 10 years after we published a paper. a paper in which we put everything into atoms. We went to the lowest scale of 2 dimensions, which is atoms. And we were not celebrating the paper. I mean, he came to Mexico and we were having some wine, you can see. Very good, by the way. And because we published this paper in 1991 in August, before carbon nanotubes. Paper of JIMA of carbon nanotubes was 1991. And Endo's paper was in 80s, but I mean, I didn't know about that. And it turns out that, okay, let's put atoms on the periodic surfaces, periodic minimal surfaces. And the trick is to introduce heptagons or octagons. If you introduce heptagons or octagons, you give the saddle shape that it is needed to decorate the surfaces. This is the D surface or F, and these are super nice objects. And people started to calculate things. People from Cornell, Thomas Lenowski, and Veit Elser immediately took the idea and published a Nature paper using DFT and calculating the properties of this one, not this one, because this was found later, well, in carbon, and these were, they call these Schwarzschild. The minimal surface decorated with carbon, they call Schwarzschild because to honor Hermann Amadeus Schwarz. I'm going to show you something very interesting regarding with graphene. I mean, people have tried to synthesize these Schwarzschilds. And this is one attempt, I believe, with reduced graphene oxide. And they have found this material, which the Poisson ratio is almost 0. 0 Poisson ratio means that when you deform the material, you squeeze the material usually tends to expand in perpendicular direction, but this one does not expand. It's like cork. That's why cork is used for the bottles, and this is known since a long time ago. You cannot use any material to close a wine bottle, right? Think about it. So Ray Bowman called me, oh, Humberto, we have a problem. We have a graphene sponge, and I want you to do calculations to have 0 Poisson ratio. And he sent me this, and this is 5 microns. This is 5 microns, this is millions of atoms. I couldn't do that, but I proved that it was possible to change the curvature and get almost 0 Poisson ratio. And then this motivated me to have something that has negative Poisson ratio and is stable, because this is a criterion. I didn't publish the paper. I have the coordinates somewhere. Could be good to try here. I mean, to try here at least with the mechanical properties. So I will show you animations. I hope this, I don't know how these should, okay. These animation, these are a film. This is for Jimena because she likes to put things on fire. I mean, this is carbon. So stands fire more or less. You cannot leave it all the time because certainly it will form CO2 and then goes. But this one, you can see that the Poisson ratio is very small, and you can squeeze these, and thus it goes to the same shape, original size. So it was interesting. An interesting material. And now I will switch gears to something very cool. Now graphene, this is atoms, right? And we started to work when I started working with molybdenum sulfide and tungsten disulfide, we were working fullerenes and tubes. And we calculated the properties of tubes. And we were the first group to predict that these structures, the tubes, because nobody was interested in flat things. At that time, when fullerenes and nanotubes, everything was fullerene nanotubes. Now we are going back. That's the way things work. And but at that time, I mean, this was more than 20 years, we knew that molybdenum sulfide, tungsten disulfide, molybdenum diselenide, tungsten diselenide are semiconductors and have this structure. You can have the trigonal prismatic, which in projection looks like a honeycomb, or you can have the octahedral phase, which is less stable. This is a metal, and this is a semiconductor. This is very important because graphene is not a semiconductor, it's a semi-metal with all the properties that electrons have, which are super nice. But here we have a semiconductor, which also is non-centrosymmetric. And when you have a semiconductor with a direct band gap, and I will show that, which is centrosymmetric, you can have super interesting electronic properties or optical properties. So here I didn't include the spin-orbit coupling. I will talk a little bit about that, but this is the band structures, direct band gap. This is the valence band, conduction band. Bulk is indirect band gap. We have a non-centrosymmetric monolayer, forms 3 atoms thick. This has a very important nonlinear optical property, which is called second harmonic generation. We, unfortunately, if you think about it hard, linearity is the exception. Nonlinearity is what, I mean, if you want to understand the brain, we have to understand more about nonlinearity. If we want to, we always use the Schrodinger equation, linear Schrodinger equation, but there is the nonlinear Schrodinger equation. Nonlinearity is harder, but lots of problems in nature are nonlinear. And here we have this material. This is BBO, barium beta borate, that is known for since a long time ago, has, of course, is non-centrosymmetric material. And the interesting thing of this second harmonic generation is you have 2 photons, and these are the 2 photons. And you shine a laser, and the laser will, once the laser goes out of the material, the wavelength will be half, or the frequency will be two times the times the one you use first. So here is red goes from red to blue, and this is super cool. And it turns out that if you calculate the nonlinear optical susceptibility, which is called chi2, the chi2 of these materials is 3 orders of magnitude the one of BBO, which is super interesting. This is the nonlinear susceptibility. I'm going to take into account these components and the way they are using it, but this is the TMDs, layer materials, monolayers, and you compare with BBO. And this is important because nowadays you can use, and people are using BBO with another nonlinear optical property, which is the parametric down conversion, which also you can use BBO. You shine a laser with frequency 2 omega, and then you get 2 photons, and these 2 photons, you can entangle the photons, and you can do photon entanglement. So I believe in the future we will use these layer materials for photon entanglement. And remember that the Nobel Prize last year was given to photon entanglement. And this year, who knows, right? Perhaps quantum computing or something like that. I don't know. Okay, just super quick, a little bit of solid state physics. But one interesting thing of these semiconductor flat structures, and now I'm trying to convince Juan Jose and my brother Mauricio to synthesize tubes again, because I'm sure now with all the experience, 20 years, we can find interesting optical properties. But it turns out that there is an effect of the interaction between the spin of the electron and the nucleus, which is called spin-orbit coupling, that separate the bands here and produce just two transitions from the valence band to the conduction band. And these are called A exciton, one transition, and the other one is B exciton, because excitons are electron hole pairs. Once you have moved an electron from here, you leave a hole, and this behaves like a hydrogen atom, where you have your charge, and you have this negative charge, and you have your positive charge. And these are really very tightly bound. So you can do excitonic physics with this, and people are doing that. Now, what I'm doing here regarding biology, there are people working on biology. This is a different thing, but this is something to think about it, where we need to, to work, or we can work with two-dimensional materials. If you change the surface of these two-dimensional materials, because these are pure surface according to the definition, the thickness is very small compared to the surface, and you change the surface, you can use this as a detector. And we have used that. In this case, this hydrogen, a oxygen atom, but this is just for the picture. But we have used manganese, and we have a dopamine paper, and we have this two-dimensional material that can detect dopamine, and also other biomolecules, which are very important. Cortisol for the stress, you are very stressed. Adrenaline, of course, when you are also excited. And this is a pocket. It works with the battery. And you just spit on that. I mean, it has just saliva, or don't spit, I mean, just saliva, right? And you can sense, in this case, with dopamine, it worked, but it should work with the others. We are working on that. I want to introduce for my team, Trevor Rohn, who is doing the machine learning, my super student, Zach Ward. He is now my postdoc. He's super clever, super good. Aida Ebrahimi, she's from Iran at Penn State, excellent. I mean, she's the one who's doing all this, the electrochemistry of this. And my brother is my brother Mauricio, who sometimes comes here. The last thing, okay, 1 minute late. This 1 minute deserves. One thing that I find super interesting is you generate a defect in this material, which hexagonal boron nitride is like graphene, one atom thick, in which the boron and nitrogens alternate. You generate a defect. In this case, this is called NBBN, because you should have a nitrogen here, vacancy of nitrogen, and this atom, which should be boron, is exchanged for nitrogen. I mean, this is an invention. But people think that this defect is the responsible of this super sharp peak in the photoluminescence. This is a technique that you shine a laser and on your material absorbs and responds with this super sharp peak. Remember, one thing that I have not told you is that hexagonal boron nitride band gap is 6 EBs. So you shouldn't have, if you don't have a defect, this should be flat. You have a defect, you have this peak and these other peaks, but this one is super big. And when you do measurements and calculate something which is called G2, the second order autocorrelation function, and measure this, you find that this material emits photons one at a time. It's like having a rifle of photons. Then another photon, not all the photons as we are used to. And this is very important. It's going to be very important, in my opinion. The challenge is vacancies are reactive, is to find a defect and control the defect. So you can control the emission where you want the emission. I know people want this for encrypting, and which may work for detectors. I'm interested in detectors, in sensors. So, and this is just for the lovers of band structures, which I am one of them. This is called the NVVN defect because you have a vacancy of nitrogen, and then this nitrogen, this should be boron, and you substitute this with nitrogen. And these are the possible transitions that you can have from the valence band to the conduction band. If you don't have the defect, you don't have these levels, these mid-gap states, nothing happens. So you need to do defect engineering. And I find this is super cool. As the surfaces, getting these 35 genus structures printed, calculate and measure the mechanical properties and also the properties is also super cool. Now we are going back to the flat thing, and I think we should go. I mean, you should go back to the nanotubes made of hexagonal boron nitride, because there were nanotubes, and also molybdenum sulfide, all these 2D materials. So, and with that, I change. National Science Foundation provides the money. Supercomputing, you need supercomputers sometimes. Oh, by the way, at RPI, my university, we will be the only university in the US, and I think in the world, who will have a quantum computer very soon. Well, they don't tell you, but IBM is going to donate a quantum computer. You are interested in doing quantum computing, that would be, you are welcome. And gracias. Thank you very much. Questions?